Okay, this is discussion 8.1, which is an introduction to acids and bases. So we're going to talk about how we define acids and bases, and we're going to solve some simple problems that show the relationship between hydrogen ion concentration and pH. Alright, so properties of acids. Physical properties. They produce hydrogen ions in water. Really, they produce hydronium ions. So a hydronium ion is just a hydrogen ion attached to a water molecule. We'll talk about that a little bit more later. They taste sour, they're good electrolytes, and the pH is less than 7. Chemically, they react with bases to form water and a salt, and they react with certain metals to produce hydrogen gas, and they react with carbonates and bicarbonates to produce carbon dioxide. Finally, they turn blue litmus paper red. You can kind of remember that because red, acid, they sort of rhyme-ish, but as long as you remember they turn blue litmus paper red, doesn't really matter how you do it. Okay, so let's talk about properties of bases. Physical properties of bases. They generally produce hydroxide ions in water, although not always. They taste bitter and chalky. They are good electrolytes. They feel soapy and slippery. And the pH is greater than 7. So a lot of the common acids are in foods. Bases are typically not edible, although there are some. These are usually cleaning products. And chemically, bases turn red litmus paper blue. Base and blue both start with B, so that's how you can remember that. And they react with acids to form water and a salt. Okay, so when we recall the pH scale, pH, acidic is less than 7 and basic is above 7, so pH of 7 is neutral. Now you might remember from Chem 1 that pH plus pOH equals 14. So if the pH is low, that means the pOH is high. And we'll also talk about how these relate to hydrogen ion concentration and hydroxide ion concentration. Just to give you sort of a sense of what typical pH values might be, here are some common things. So 1 molar sodium hydroxide has a pH of 14, and 1 molar hydrochloric acid has a pH of 0. Typical acids that you might see commonly, like vinegar, lemon juice, stomach acid, those are between pH of 2 and 3. Ammonia is a typical household cleaner, 12, somewhere around there. And then things that are close to neutral, pure water has a pH of 7. Blood is slightly basic, but again, pretty close to 7. And milk is slightly acidic. So let's look at some examples of neutralization. An acid will neutralize a base, which produces salt and water. Here are some examples. The most common one you've seen a lot is hydrochloric acid and sodium hydroxide, producing sodium chloride and water. And then here's a variety of other examples. This is sulfuric acid and sodium hydroxide. This is diprotic, which means it has 2 H pluses. And so obviously we have to take that into account when we balance it. Phosphoric acid is triprotic. And then this calcium hydroxide is an example of a base with 2 hydroxides, which again, we have to take that into account when we balance it. When we say a salt, we don't necessarily mean sodium chloride. We just mean the ionic compound that's formed from the base and the acid. So the cation comes from the base and the anion comes from the acid. And the standard enthalpy change of neutralization, we've already sort of calculated some of these. But the standard enthalpy change of neutralization is the energy change associated with the formation of 1 mole of water when a strong base reacts with a strong acid under standard conditions. So that's how we're defining it, is by the formation of 1 mole of water. So the standard enthalpy change of neutralization for this first reaction would be calculated based on this. Here we'd have to multiply all the coefficients by 1/2. All right, now we've already talked about acid-base reactions a lot, and we'll continue to do so, and that's because they're a really good way to study a lot of different chemical phenomena. For example, I mean, if you just think back to all the labs you've done in Chem 1 and so far this year, how many times do you use acids and bases? I mean, nearly constantly. As far as hydrochloric acid, you use it a lot, sodium hydroxide. All neutralization reactions are exothermic, so they can be useful for studying enthalpy changes. They all follow a general formula, so they're kind of predictable. And we can look at acid-base reactions as equilibrium systems. So we'll talk more about this in the next topic, but weak acids and bases are systems at equilibrium, and strong acids and bases have reactions that go completely to the products. They also have really important environmental significance. So you've probably heard of acid rain. Now you might or might not know that normal rain is acidic. The value of normal rain for pH is 5.6 or greater. And the reason that it's still less than 7 is that there's dissolved carbon dioxide, but that's not considered to be a contributor to acid rain. Because acid rain has a pretty specific definition. Acid deposition produces rain with a pH of less than 5.6. So let's talk about what causes that. This is caused by nitrogen and sulfur oxides. So vehicles produce these, different industries produce these as products of combustion. It's just a couple examples, and there's more in your textbook in Chapter 8. Nitrogen dioxide plus water gives nitric acid, and it could just be reacting with water vapor in the air. Sulfur trioxide and water vapor gives sulfuric acid. So obviously those are both strong acids that could lower the pH of rain. Now that we have some strategies we use to combat acid deposition, there's pre-combustion methods and post-combustion methods. So remember we said that these are produced by combustion reactions in vehicles and in different industries. So pre-combustion methods basically means doing something with these chemicals before they have the opportunity to combust and form these oxides. So again, we would just be using some of these techniques on fuels before we combust them. An example of this is the physical cleaning or mineral beneficiation of coal. So basically what they do is they crush coal and then they use flotation to be able to remove some of the impurities. And so they're just cleaning the coal before it's actually combusted. Post-combustion methods are techniques that use technology to remove these oxides, also heavy metals and dioxins, before they're released into the atmosphere. So one example of this is the use of lime, which is calcium oxide. And so we can react it with sulfur dioxide to produce calcium sulfite, which then prevents the sulfur dioxide from going into the air and reacting with water vapor and contributing to acid deposition. So this is just a really, really short overview of that, but definitely worth reading more about in the textbook. All right, so let's talk about the definition of acids and bases. And I think when we think of an acid, we think of hydrochloric acid, and when we think of a base, we think of sodium hydroxide. We think of these because we use them all the time, but also they fit into all definitions of acids and bases that we have. And so we think of acids as containing hydrogen ions and bases as containing hydroxides. But there are much more broad definitions of acids and bases that don't have H or OH as a requirement. So there's three major models and definitions: the Arrhenius model, Bronsted-Lowry, and Lewis. Now, you're only going to be assessed for IB on the last two, but I think it's important to talk about all three since they sort of represent a gradual broadening of our understanding of acids and bases. All right, so the Arrhenius definition basically says that acids are substances in water that increase the concentration of hydrogen ions. Bases increase the concentration of hydroxide ions. Now, this is actually a very useful definition, even though it's pretty narrow, because it's really easy to sort substances into acids and bases using this definition. The problem is that many bases in particular don't actually contain hydroxides, and certainly there are acids that don't contain hydrogen ions as well. So the Bronsted-Lowry definition is broader. In the Bronsted-Lowry definition, an acid is some kind of species, be it a neutral molecule, anion, cation, that donates a proton, or an H+. And a base is a neutral molecule, anion, cation, etc., that accepts a proton. So this is sort of the general formula where HA represents any acid, B represents a base, and the acid donates the proton to the base. So then we form HB plus and A minus. Now, we have to notice the change in the charge. Since it's an H plus that's moving, when the H plus is donated to the base, it's going to increase the overall charge by 1. Since the acid is losing an H plus, it's going to decrease the overall charge by 1. Okay, so a more specific example would be hydrochloric acid and water. And now, we're going to see this a lot, actually. Water is technically acting as a base here because it's accepting a proton from hydrochloric acid. So when hydrochloric acid donates the proton to water, we get H3O+, the hydronium ion, and a chloride ion. Now, if hydrochloric acid is our acid and water is our base, we're going to form something called the conjugate acid and the conjugate base. So let's talk a little bit about those in a minute. So this is an operational definition, which means that the classification depends on how the substance behaves in a chemical reaction. So it's possible, as a little preview, that something could behave as an acid in certain circumstances and a base in other circumstances. So let's talk about these conjugate acid-base pairs. A conjugate base is what remains after an acid has donated its proton, and a conjugate acid is what's produced after a base has accepted a proton. So a conjugate acid-base pair will differ by 1 H+, no more, no less. So it's a really common question on IB to ask which of the following represents a conjugate acid-base pair, and you're just looking for two things that differ by 1 H+, so don't be tricked by that. All right, so for example, HA, our general form for an acid, and A- are a conjugate acid-base pair, where A- is the conjugate base that's formed by acid HA. And B and HB+ are a conjugate acid-base pair, where HB+ is the conjugate acid formed by the base B. Now, let's look at these conjugates. A- is a conjugate base, and now it could accept a proton, so that's why it's a base. HB+, now it could donate a proton, and that's why it's an acid. So here are some examples of Bronsted-Lowry systems. Now in the first three examples, you'll notice that water is acting like a base because it's accepting a proton from the acid in each case. In the last two examples, you'll notice that water is acting as an acid because it's donating a proton to the base in each case. So we're seeing that water can behave as both an acid and a base. So we need to identify a couple terms. The first term is amphiprotic, and that means that it's something that can act as a Bronsted-Lowry acid or a base because it can donate a proton, or it can accept a proton. A more broad general term is amphoteric. This just means a substance that can act as an acid or a base, not necessarily narrowly in the Bronsted-Lowry definition, but in any of the definitions. We've also seen the hydronium ion several times now, so I just want to make sure we highlight that. The hydronium ion is H3O+. We use this pretty interchangeably with the hydrogen ion, especially when we do calculations. For example, this is produced when we show hydrochloric acid in water. Now, this is a case where you'd really want to write out the hydronium ion because we're trying to show what happens with hydrochloric acid and water specifically. So hydrochloric acid donates a proton to water, and we're left with H3O+ and a chloride ion. Okay, so take a moment to do this practice. Pause here. Try to list the conjugate bases for each of those acids and the conjugate acid for each of those bases. Okay, let's check. All right, so when hydrochloric acid donates a proton, what's left is a chloride ion, so that's its conjugate base. Now, notice in phosphoric acid here, when we write the conjugate base, we're just showing it having donated one proton only, not all three. Okay? Now, let's look at these conjugate acids. So now we're showing that the base has gained a proton. And notice how we're changing the charge here. When it gains a proton, the charge goes up by 1. Now, HSO4-, that would be a great example of something that is amphiprotic because it can gain a proton to form sulfuric acid or lose a proton to form the sulfate ion. Okay, let's talk about our last definition of acids and bases, and that's the Lewis definition. He is basically a celebrity. You may remember him from such hits as Lewis structures. All right, so in the Lewis definition, an acid is an electron pair acceptor and a base is an electron pair donor. So this is something that we've already talked about ammonia as a base, but boron trifluoride is not something you would necessarily think of as an acid in any other definition. But in this definition it is because it can accept an electron pair. Since boron is electron deficient, it only currently has 6 electrons, that's what makes it a good acceptor. So ammonia will donate a proton to form a dative bond with boron trifluoride. And so we create this structure, and that's a dative bond in between the boron and the nitrogen. So when we think back to where we've seen this behavior previously, hopefully what comes to mind is talking about the formation of coordination compounds. So when a ligand bonds to a metal ion, this is also a great example of a Lewis acid-base system because the ligand is an electron pair donor, so it's acting as a Lewis base. The metal ion is acting as a Lewis acid because it's accepting the electron pair. So a really common question would be to ask, which of the following is an example of a Lewis acid-base system but not Bronsted-Lowry, and the formation of a coordination compound fits the bill perfectly for that. All right, so let's talk about the relationship between pH and concentration. Now, we know that, hopefully, that pH is the negative log of the concentration of the hydrogen ions. Now, remember that these brackets mean concentration. Since we're using that more or less interchangeably with hydronium, we can say that pH is also equal to the negative log of the hydronium ion concentration. So if we sort of undo that and solve the hydrogen ion concentration, we can find that the concentration of hydrogen ions is equal to 10 to the negative pH. Now, P is just an operator that means negative log. All right, so similarly, POH is the negative log of hydroxide ion concentration, and again, we can solve to get the hydroxide ion concentration is 10 to the negative POH. Okay, you could do that for anything. We're going to see this in other places. In the next topic, we'll talk about pKa. That's the negative log of Ka. You don't necessarily know what Ka is yet, but you know that P means negative log. P elephant is the negative log of elephant. That makes no sense, but it doesn't matter because P means negative log. And remember that pH plus POH equals 14. This will help us solve some problems that we're going to come across. All right, so let's use the pH equation to figure out some simple problems. Now, because it has a logarithmic relationship, if I have a 1 unit change in pH, that corresponds to a 10-fold difference in concentration. So for example, if I have a hydrochloric acid solution with a pH of 2 and I wanted to compare that to a solution with pH of 4, the solution with pH of 2 has 100 times more hydrogen ions in it. All right, so more concentrated acid has a lower pH, more concentrated base has a higher pH. All right, try to complete these sentences. Okay, so pH 3 and 4 have a 10-fold difference since it's just one pH unit. So a solution of pH 3 has 10 times more hydrogen ion concentration than pH 4. pH 2 and 5 are 3 units apart, so pH 2 has 1,000 times more H+. And when I compare 3 to 1, pH 3 has 100 times less H+ than pH 1. Note that it's less because the pH is going up. Okay, this is a sample IB problem. So I want you to take a second, pause, and see if you can rank these in order of increasing pH. Okay, now we have 2 acid solutions and 2 base solutions. So 1 and 2 are acid and 3 and 4 are base. So we know that the first 2 will go first. All right, so we have to figure out which has the lowest pH. So the more concentrated acid solution will have the lower pH. So we know that 1 has the lowest pH followed by 2. So we're looking at choice A or B. Now, when we compare 3 and 4, that's when people sometimes get tripped up. Because remember, the more concentrated the base, the higher its pH. So 3 is actually going to be the very highest because it's the most concentrated base. So the correct answer here would be B, 1, 2, 4, 3. Okay, try one more problem. Okay, this is a 4-fold difference. So the pH solution, the pH of the solution with the pH of 2 is 10,000 times more concentrated than the solution with a pH of 6. Okay, let's look at some calculations. Now, these are not too tricky, but you really have to think your way through these carefully and try to think about what's going on. All right, so we're going to try to determine the pH of a solution that results when I mix 100 milliliters of 0.5 molar hydrochloric acid with 200 milliliters of 0.1 molar sodium hydroxide. So the first thing I have to ask myself is this complete neutralization or do I have excess acid or base? So the easiest way to do this is to find the moles of each of them. So let's find the moles of acid first. Now this is also monoprotic and this only produces one hydroxide. So the concentration of the solution will be the same as the concentration of H+ and sodium hydroxide. All right, so to get the moles of acid, I take the molarity times the volume. So 0.5 moles per decimeter cubed times 0.1 decimeters cubed. So I have 0.05 moles of acid. I'm going to do the same thing for the base, and I'll get 0.02 moles of base. Okay, so I have more acid than base. All right, so let's figure out how much excess I have, and then I'm going to use the new volume to calculate molarity and pH. So I just subtract them, and I find that I have 0.03 moles of acid that were not neutralized. Now, I mixed 100 milliliters with 200 milliliters, so my new volume is 300 centimeters cubed, or 0.3 decimeters cubed. So, to calculate the concentration of acid in the new solution, I take moles divided by decimeters cubed, and I get 0.1 moles per decimeter cubed. Since pH is the negative log of the hydrogen ion concentration, I can just take the negative log of my answer here, and I get that the pH equals 1. Okay, now here's another problem, and this asks for 4 different things. We have to make sure if we answer a question like this that we clearly write and label all 4 answers. So it wants the pH, pOH, hydrogen ion, and hydroxide ion concentration for a 0.01 molar solution of sodium hydroxide at 298 Kelvin. So we already have the concentration of sodium hydroxide, and since there's only one hydroxide ion produced for every molecule of sodium hydroxide, I know that the hydroxide ion concentration is going to be 0.01. Okay, now, I also know that the pOH is the negative log of the hydroxide ion concentration. So I can solve for the pOH and I get that it equals 2. We know that pH plus pOH equals 14, so the pH is 12. And then, since the hydrogen ion concentration is 10 to the negative pH, I know my hydrogen ion concentration is 1 times 10 to the negative 12. And there should probably be some units on there. It should be moles per decimeter cubed. Don't leave it unitless like I did. Okay, now let's look at one final problem. And this is 200 milliliters of 0.1 molar hydrochloric acid mixed with 100 milliliters of 0.5 molar hydrochloric acid. So, important note here, this is not a reaction. This is just mixing 2 solutions of different molarities and trying to find the resulting molarity and pH. Okay, so let's figure out the moles of acid in each solution and thus the total moles of acid. All right, so in the first solution, when I take molarity times volume, I get 0.020 moles, and in the second solution, I get 0.050 moles. So it's HCl in both cases, so I'm not subtracting here because nothing's being neutralized. I'm going to add my moles together, and I know that I have a total now of 0.070 moles of acid. Okay, now I have to figure out my new volume. I have a total of 300 milliliters, or 0.3 decimeters cubed. So now I can calculate my new concentration, moles per decimeter cubed, and then I can solve for the pH, and I get 0.64. Okay, that's the end. Make sure you practice and come to class with lots of questions.